Okay, so now we're going on to Newton's law of universal gravitation. He has so many laws. He's like a police state. For this topic or for the law? Just for the law, no, it's very short. Yeah, it isn't too hard to understand. If you have, so any two objects with masses m1 and m2 exert equal and opposite gravitational force on each other. They don't have to be opposite in any way. They just have to both have mass. Equal and opposite gravitational force. It's always an attractive force. Like, ooh, look at that force. I'd like to get to know that force better. And the magnitude of this force, so we know the direction is always away from the chosen body toward the other body. They're pulling on each other. It's like a pulling force. F is equal to capital G times the mass of m1 and mass m2 divided by r squared. Yes. Where G is the universal gravitational constant. That's 6.67 times 10 to the minus 11 Newton meters squared per kilogram squared. And r is the distance between the two objects. Yep. Well, yeah, they don't believe that there's such a thing as gravity. They do? I've never heard that one. I think they believe different things. Some of them just believe, like, I don't know, it looks pretty flat. Okay, so here's a couple things to notice about this. Yeah, times 10 to the negative 11. Right. Yeah, exactly. Well, first, force does depend. So the gravitational force on an object does vary linearly with its mass. So I wasn't lying to you about that. Yeah, for now we're thinking particles, and yes, it is the centers of mass. Yep. The centers of mass, that's right. Yep. That's right. And everybody in here is exerting gravitational forces on each other, but they're so, so small. But they can be measured with coolest experiment. I mean, the coolest experiment. And so I'll talk about it, but it's called the Cavendish Experiment. And we actually have it set up in the lab, but it's a very complicated experiment that takes a long time to understand, and so we never got into it. But it's sitting up on top of the cabinet, a way to measure what you're measuring really is that gravitational constant B. It's two lead it's two little lead balls and one like big 10-kilogram lead ball, and the two little ones are on just a skinny little wire, thread, and you displace that thread, and it just barely, it's so thin, but it just barely tries to get that thing back in place, and it overshoots and does this very slow oscillation that takes like an hour to swing back, or 20 minutes or something. But I mean, like not like seconds, but like parts of an hour, and that's true. But then the rate of oscillation is affected by that, because the force of that restoring force is so little on the wire. That attractive force of the 10-kilogram mass actually affects its motion, and based on curve fitting, basically, like you can figure out what that constant is. And so somebody measured that universal constant of gravitation in like 1800 or something. It's amazing. That's Cavendish. Yeah, it's amazing, and to see it work is amazing. Okay, so that's what I said before. But what I didn't say before is that this gravitational force also depends on the distance between the objects. Right, so we'll talk about that, and that well, it's still conservative. Yeah, it's still conservative, but it's not constant. So the potential energy then is well, it's like the derivative with respect to negative derivative with respect to r of this. So negative g m1 m2 over r to the negative third, right? No. Over r. How does that work? Okay, that's not what I said anyways. So it does depend on the distance between them. And up until now, we've been saying that no matter how high the object is, or in other words, how high the how far the object is from the Earth, gravity pulls on it the same amount. So let's figure out, so why have I been saying that? And presumably we've been getting pretty good results, you know? Yeah, right. The farther you get from the center of the Earth, the farther you get from the center of the Earth, the less it's pulling on you. That's right. So if you're in a spaceship in orbit, you know, orbit depends on gravity. So obviously you're not really free of gravity, but gravity is less as you get farther away. Okay, so why do we usually treat the gravitational force as independent of the height? Hey, listen. Hey, see you tomorrow, right? Yeah. What? So why do we usually treat the gravitational force as independent of the height?
Radius of the Earth is so big.
Yes.
That if you move it, okay, but relative, like the climb to the mountain is like tiny in the scale of the space.
So let's just figure out what the difference is as you move a mile vertically. Yes. So how much does the gravitational force change if the height changes by a mile?
Well, the diameter is 3,963 miles, or the radius, sorry.
So let's say 1 mile above the surface of the Earth. What did you say? Did you just know what the radius of the Earth is?
No, it's in my
plan. Oh, okay. I thought it was amazing. Now I realize it wasn't amazing at all. Okay, so at the surface of the Earth, the force is the gravitational constant times the mass of the Earth. I'm going to call that m. Times little m, divided by the radius squared, and the radius of the Earth is 6.371 times 10 to the 6 meters. We're squaring that. So now 1 mile above the surface, one mile above the surface, we still have the g, the mass of the Earth, the mass of the object, but now the radius is 6.371 times 10 to the 6 plus 1609, and that's all squared. So that's what, oh yeah, so for all you guys who run mile, that's how a true mile is 1609.344 meters. So you run 1,600 meters, so you're 9.344 meters short of a. So actually, I think every race for the rest of the season, you should just keep run right through the tape for 9 more meters and then stop your watch. That would be like a totally studly move. And everybody's like, oh no, I'm running the mile today. Yeah, I won the mile. Yes? That's the G value. The radius of the Earth is this. Yeah, I wouldn't know that. It's in my notes. There was a guy from Burnsville. You guys you wouldn't remember this, I guess, but I think it was about 2008. Rob Finnerty, yeah. And he ran the state record for the 1,600 meters in 3:59 for 1,600 meters. And at that time, only 4 people in American history had ever run sub 4 minutes for the mile in high school. But that was for the 1,600 meters, and if you do the standard conversion for how long it would have taken him for the last 9 meters, his time was like 4:01 point something, and so he just missed it. He had to lose her, exactly. He was pretty fast. Okay, so let's figure out the ratio then, so Fs over F mile, a lot of this stuff cancels out, and you just end up with 6.371 times 10 to the 6 plus 1609 whole quantity squared over 6.371 times 10 to the 6 squared. And you get that the force of the surface is 1.00051 times the force a mile above the surface. So up to a lot of precision, even a motion of a mile vertically doesn't have any significant effect on the strength of gravity. Any questions about the thought process there? So all the M's and the G all canceled out, and we just got left with that stuff, and that comes out to be basically 1. If it was 1, then they would be exactly the same. Yep. Yeah, so the thing that affects it more than altitude is apparently just geological formations. Uh-huh. Yeah, and then if you're close to mountain ranges or something, I think gravity is higher. But yeah, it does vary a little bit. Uh-huh. Yeah, exactly. Yeah, exactly. That'd be a good idea. Let's go. I pole vaulted 10'6". Yes. It's not that good, but yeah, it's pretty dangerous. People get hurt pretty badly. Okay, let's okay. Well, we know that. So it's still a conservative force. So there has to be a potential energy function. And we know that the force, G big M little m, over R squared has to be equal to the negative partial derivative with respect to r of u. And so we can integrate this, and we get that the potential energy function is, whoa, that was crazy. Potential energy function is negative g, big M, little m over r. And so let's figure out what are we going to do first. So let's use this to figure out the escape velocity if we ignore air resistance. Yeah, to never fall back down. How fast do you have to jump so that you never come back down? Yeah, because I know I've jumped 3 meters per second before and I came back down, so it's more than that. Okay, so think for a second. Okay, so we're going to use conservation of mechanical energy. So at instant 1, we're at the surface of the Earth with some speed v. So the kinetic energy is 1/2 mv squared. The potential energy at instant 1, we're at the surface of the Earth, so this is going to be g times big M times little m over the radius of the Earth squared. And at instant 2, we're talking about the highest point this thing gets to before it starts to come back. So what's the speed at that instant? 0, yep. So kinetic energy is 1/2 mass times 0 squared, so 0. And the potential is, so that's going to be the distance r, like how far away you are. Maybe I'll call it h. You know, that's that highest height. Oh, these are supposed to be negative. Because that's what the potential energy function is. This is the potential energy function. Oh, and it also shouldn't be squared. Sorry, I was thinking of the force. This is the potential energy function. So, yeah, that's a good question. So when do we need to use this? We need to use this anytime you're talking about distances that are much bigger than the object is way away from the surface of the Earth. You know, if your distance from the surface of the Earth is at least on the order of magnitude of the radius of the Earth, then you have to use this approach. So we'll use it mostly for planetary motions, satellite orbits, that kind of stuff. Okay? For things that are far away from the surface of the Earth. If you're just talking about motions near the surface of the Earth that are the order of magnitude of like our daily experience, you can still use the old approach. It's a good approximation. Okay.
You were saying that for instant 2, potential energy is just h. Why?
It's not h, the distance is h. So this is going to be negative g, big M, little m over h. So h is how far away the thing gets before it starts coming back down. So conservation of mechanical energy says 1/2 mv squared minus g big M little m over the radius of the Earth is equal to 0 minus g times big M little m over h. And we can cancel out the little m's. There's one of those in everything. And multiply everything by 2. And we get that v is equal to the square root of 2g big M over RE. Yep, minus 2g big M over h, all square root. So this tells you how fast you have to be going to get to some certain distance from the Earth. Yes? Oh, it won't matter, but that's a good thought. So I guess we're saying that h is a distance from the center of mass, the center of mass of the Earth, the way I have it written there, instead of a height above the surface. Otherwise, yes, you're exactly right. Question? That's the mass of the Earth. So this is general for any body. So your escape velocity from a small mass would be very small. Yep. And now we'll take the limit. So the escape velocity is the limit as h goes to infinity, because we don't want to ever reach that highest point where it starts coming back down. RE is the radius of the Earth, and h is a general distance from the center of mass of the Earth to the object.
So the first experiment, it's RE because it starts on the surface.
Yep.
That's
right. Okay, so what's the limit of that square root as h goes to infinity?